Every single AI chip running right now, every H100, every H200, every GPU inside every data center on Earth is fighting a war. It's slowly losing. Not against a rival company, against heat. The single biggest limit on how fast these chips can run isn't the silicon itself. It's how much heat that silicon can survive before it melts its own performance away. China thinks it found the material that ends that war completely. And the material isn't some exotic new invention. It's the same thing sitting in an engagement ring. Here's the claim you've probably already seen. China replaced silicon with diamond, and just made Nvidia's most advanced chip obsolete. That headline is almost right, and almost completely wrong at the same time. And the actual truth sitting underneath it is genuinely more interesting than either version. Stick with me, because there's a specific number about 90 seconds from now that tells you exactly how big this really is. And it's not the number you're expecting. Think about what obsolete would actually mean here for a second before we go any further, because that word is doing a lot of heavy lifting in that headline. Obsolete means nobody would ever choose the old thing again. It means the H100 becomes as relevant as a flip phone. That's an enormous claim to make about a chip that companies are still paying tens of thousands of dollars each for right now, today, in the middle of the biggest AI build-out in history. So either that claim is wildly overblown, or something genuinely seismic just happened in a lab most people have never heard of. By the end of this video, you'll know exactly which one it actually is. Let's start with why heat is even the problem in the first place, because this is the part most coverage skips completely. Silicon starts losing its ability to function properly once it gets too hot, and modern chips pack so much processing power into such a small space that heat builds up faster than most cooling systems can pull it away. That's exactly why AI data centers need massive cooling towers, and why some of the newest chip designs are already flirting with liquid cooling and even more extreme methods just to stay alive under load. Every watt spent moving heat away from a chip is a watt not spent actually computing anything. Heat isn't a side issue in modern chip design anymore. For the most advanced chips on Earth, it's arguably the single biggest bottleneck standing between where performance is today and where it could be tomorrow. Here's a number that makes this concrete. Data centers running today's AI chips at full tilt can require entire dedicated power substations just to keep cooling systems running around the clock. And industry estimates suggest cooling alone can account for a meaningful chunk of a data center's total electricity bill, separate from the power actually spent on computation itself. That's money and energy being spent purely to fight heat, not to train models or answer your prompts. Solve the heat problem properly, and you're not just making chips faster. You're making the entire AI industry's electricity bills smaller at the same time. Diamond solves that problem in a way almost nothing else on the periodic table can. Its thermal conductivity can exceed 2,000 watts per meter Kelvin, more than 5 times higher than copper, and dramatically higher than silicon itself. Its bandgap, the property that determines how much voltage a material can handle before it breaks down, sits at roughly 5.5 electron volts compared to silicon's 1.1. That's not a small edge. That's a completely different category of material, one that can handle extreme heat, extreme voltage, and extreme power density all at once, conditions that would genuinely destroy a standard silicon chip. Now here's the part where this actually becomes a real current verified Chinese story, not just theory. In June of this year, a company called Sino Powder signed an agreement in Zhengzhou, Henan province, to build China's first fully integrated diamond semiconductor industrial chain, backed by an investment of roughly $210 million. The The plan calls for 500 microwave plasma chemical vapor deposition systems, the machines actually used to grow synthetic diamond wafers, with 200 of them coming online by the end of this year alone. Once fully ramped, the facility is projected to generate close to 3 billion yuan in annual output within 3 years, producing 2-inch and 4-inch single crystal diamond wafers specifically for power electronics, electric vehicles, aerospace systems, and AI hardware. The company's own chairman described the goal plainly, saying the project would push micro and nano diamonds out of the laboratory and into genuine large-scale industrialization for the first time. That's shock number 1. A real factory, real machines, a real timeline, not a lab paper sitting in a journal somewhere. Now here's the part that actually connects this directly to your AI chips, and it's shock number 2 in this story. Separately, a joint research team from Fudan University and Peking University achieved something genuinely record-breaking earlier this year. They successfully grew specialized light-emitting components directly onto diamond substrates, creating optical data connections that hit gigabit-per-second speeds while consuming just 0.056 picojoules per bit, a new efficiency benchmark for this exact kind of optical interconnect. Why does that matter for chips like Nvidia's? Because as AI processors get faster, moving data between chips is starting to hit the same wall that copper wiring hit years ago, where the connections themselves become the bottleneck instead of the processors doing the actual computing. And diamond-based interconnects are one of the leading candidates being explored globally to solve exactly that bottleneck. And there's a third piece, too. A separate Chinese company, Henan Kezhicheng, has already begun actual volume shipments of 3-inch ultra-thin diamond heat spreaders, specifically designed to pull heat away from high-speed optical chips, the same category of components sitting inside next-generation AI hardware. So 3 separate pieces: a factory, a research record, a shipping product. All diamond, all Chinese, all landing within roughly the same 12 months. Notice what's missing from that list too, though, because it matters just as much as what's on it. Not one of those 3 pieces is an actual finished processor, sitting in a lab, running a real workload made entirely out of diamond instead of silicon. Keep that gap in mind, because it's exactly where the honest scorecard is about to take us. If breaking a story down into what's actually verified instead of what just sounds impressive is something you want more of, that's exactly why subscribing to this channel now means you catch the next one of these the moment it happens, not after the hype cycle's already run its course everywhere else. Now here's the honest scorecard, because the title claim that this makes Nvidia's H100 obsolete genuinely overstates what's actually happening, and understanding exactly how it overstates it is the whole point of this video. What's true? Diamond's raw material properties are real, verified, and genuinely superior to silicon on multiple key measurements, thermal conductivity most of all. What's also true? Nobody, not China, not Japan, not the United States, has actually built a working diamond processor that replaces silicon as the actual computing material inside a chip like the H100. The real, current, near-term location for diamond in chips isn't replacing the silicon transistors themselves. It's replacing the material around those transistors, specifically for heat management. Here's why that distinction actually matters more than the hype headline. A diamond-powered cooling layer sitting on top of an existing silicon or gallium nitride chip doesn't require replacing an entire manufacturing industry built around silicon. It requires adding one additional, extremely effective layer to a process that already exists. That's a genuinely achievable near-term path. Building an entire diamond-based logic chip that actually computes the way silicon does, at the scale and cost Nvidia manufactures at, remains, according to researchers actively working on this exact problem, a challenge that's still measured in years, not months, largely because doping diamond precisely enough to control electrical behavior at scale remains genuinely unsolved at commercial volume. Think about the difference between those two paths for a second, because it changes how excited you should actually be about this timeline. A cooling layer is an upgrade you bolt onto something that already works. A full diamond processor is a complete reinvention of how a chip is built from the ground up, with a manufacturing ecosystem, decades of tooling, and an entire global supply chain that would all need to be rebuilt around a new base material. One of those paths could realistically show up in products within the next few years. The other one is closer to where silicon itself was, sometime in the middle of the last century. And here's a detail that quietly undercuts the China-exclusive angle of this whole story, too. Japan's National Institute for Materials Science built the world's first functioning N-channel diamond transistor, a genuinely critical step toward diamond-based computing. And that breakthrough happened in a Japanese lab, not a Chinese one. Researchers elsewhere have also already demonstrated growing thin diamond layers directly on top of existing transistors, purely as a cooling solution. Dropping temperatures by as much as 70 degrees Celsius in testing, essentially treating diamond as an incredibly effective heat blanket rather than the chip material itself, and that work wasn't done in China either. This isn't a story about China alone racing ahead of the entire world on diamond semiconductors. It's a global research race, with the United States, Japan, and China all pushing different pieces of the same underlying problem forward at the same time. And China's specific advantage right now isn't the deepest research lead. It's the fastest path to actual industrial-scale manufacturing, backed by real money and real factories already under construction. So, does this make the H100 obsolete? No, not directly, and not soon. But here's why this story is still genuinely worth paying attention to instead of dismissing outright. If Chinese diamond heat spreaders and diamond-assisted cooling layers reach commercial maturity before equivalent technology scales up elsewhere, that becomes a real practical advantage for any AI chip made using that supply chain, letting those chips run hotter, denser, and faster than a silicon-only competitor stuck using conventional cooling. That's not obsolescence. That's a meaningful performance edge. And in an industry where AI chip performance differences of even a few percentage points translate into billions of dollars, a meaningful edge is far from nothing. Here's the actual timeline to watch instead of the headline. Near term, over the next 1 to 2 years, expect diamond to show up quietly as a cooling and heat-spreading material bolted onto existing silicon and gallium nitride chips. Exactly the products Henan Kezhicheng is already shipping today. Medium term, over the next 3 to 5 years, expect diamond optical interconnects, like the Fudan and Peking University research, to start moving from lab demonstrations toward real data center hardware, specifically targeting the chip-to-chip communication bottleneck that's becoming almost as urgent as the heat problem itself. Long term, and this is the part where genuine uncertainty remains, actual diamond-based logic transistors replacing silicon as the computing material itself sit somewhere out past that horizon, dependent entirely on whether the doping problem gets solved at commercial scale, not just in a research paper. Watch whether China's diamond wafer production actually hits its own targets on schedule, because ultra-wide bandgap materials like this have a long history of promising breakthroughs that take years longer than expected to reach real manufacturing volume. Watch the doping problem specifically, because that's the actual unsolved barrier standing between diamond as a cooling material and diamond as a true computing material, capable of eventually replacing silicon transistors themselves. And watch whether Nvidia, or any Western chipmaker, starts publicly discussing diamond-based thermal solutions of their own. Because if the biggest AI chip company on Earth starts taking this seriously in its own public roadmap that tells you everything about how real this threat actually looks from the inside of the industry it supposedly threatens. There's one more thing worth sitting with before we close this out. The reason silicon carbide and gallium nitride, the two materials that came before diamond in this exact conversation, took roughly 2 decades each to go from promising lab material to genuinely mainstream product, wasn't because the physics was in doubt. It was because manufacturing at scale, cheaply, reliably, always turns out to be the harder problem than the science itself. Diamond is very likely walking that same road right now, just earlier on it. And knowing that history is exactly what separates a headline from an actual forecast. Drop one word right now before this video ends. Diamond. If you think this genuinely reshapes the next generation of AI hardware. Dust. If you think the obsolete headline is running years ahead of the actual engineering. Type it now, then go watch exactly how close China's chip-making equipment has gotten to matching the machines that actually print these chips in the first place. Because that story moves even faster than this one does, and it changes what any of this diamond breakthrough can actually be used for.